Trillions of ghostly particles are streaming through you at this very moment. These are neutrinos, and a vast sea of them fills the entire cosmos, a faint echo of the Big Bang itself. This is the Cosmic Neutrino Background, the universe's oldest unsent message. By the end of this journey, you will know the 25 deepest mysteries locked within this relic, secrets that could rewrite the laws of physics. Why has this cosmic fossil never been seen? And what happens if it holds a map to invisible dimensions? What does it truly mean to listen to the whispers of creation? This first mystery is a ghost story of cosmic proportions. The Cosmic Neutrino Background has never been seen directly, and the reason lies in the very nature of the particles themselves. Think of the cosmic microwave background, that famous afterglow of the Big Bang, as a loud and clear radio signal from the infant universe. We have been able to tune into that station for decades. The neutrino background, however, is the faintest possible whisper, nearly drowned out by the static of everything else. These relic neutrinos are so incredibly low energy that they barely interact with anything at all. 1 trillion of them pass through your entire body every single second, without a single one ever touching an atom inside you. Catching one is like trying to pick up a single, specific grain of sand on a planet-wide beach during a hurricane. The technical challenges are almost beyond imagination. Every other particle and source of radiation in the cosmos creates a deafening background noise that completely obscures this faint signal. Experiments like Ptolemy represent humanity's most audacious attempt to build a microphone sensitive enough to hear that whisper. They are trying to capture these ghostly particles in the most pristine laboratory environments ever created, cooling detectors to temperatures colder than deep space and shielding them from any interfering radiation. If they succeed, the implications would be staggering. It would be like opening a time capsule from the first second of the universe, giving us a direct look at a reality we can only currently theorize about. This detection would not just confirm a prediction. It would hand us a new set of rules for both particle physics and cosmology, rewriting our understanding of the fundamental forces that built everything we see. That faint whisper from the dawn of time carries a specific and deeply puzzling temperature. The universe has chilled the cosmic neutrino background to a frigid 1.95 degrees above absolute zero. But why this exact number, and what if it is not quite what we think it is? This temperature is not a random guess. It is a cosmic memory, a direct consequence of the universe's explosive birth and its subsequent relentless expansion. The calculation is a masterpiece of cosmological deduction. We know from the afterglow of the Big Bang, the cosmic microwave background, that the early universe was a searing hot soup of particles. As the cosmos expanded and cooled, neutrinos were the first to decouple, to stop interacting with other matter, and essentially freeze out from the primordial fireball. This moment of decoupling locked in their properties, including their temperature. The math is precise, tracing the expansion history and the physics of particle interactions all the way back to that first second. Yet, this prediction of 1.95 Kelvin rests on a foundation of assumptions that might be perfectly correct, or might be subtly wrong. A deviation of even a tiny fraction of a degree would be a scientific earthquake. Think of a perfectly insulated ice cube cooling in a vast room. You can predict its temperature drop with great accuracy, but if you measure it and find it is just a little bit warmer than expected, you know something is wrong. Perhaps the room is not as cold as you thought, or maybe the ice cube itself is generating a tiny amount of heat. In the case of the neutrino background, A temperature that does not match our prediction could mean that these ghostly particles are not as stable as we believe. They might be slowly decaying into even more mysterious particles over billions of years, releasing a faint energy that keeps them slightly warmer. Or it could be evidence of their secret conversations with the universe's greatest mystery, dark matter. If neutrinos are occasionally bumping into invisible dark matter particles, that interaction would transfer energy, altering their final frozen temperature. Finding the true temperature of this ancient relic is not just about checking a box. It is about testing the very laws we use to describe the universe's infancy. A single, precise measurement could reveal cracks in our most fundamental theories, pointing toward a reality far stranger than we have ever imagined. This temperature mystery is deeply entangled with another profound puzzle, the very identity of the neutrino itself. We know these particles have mass, but we do not know how that mass is arranged, a problem known as the neutrino mass hierarchy. Think of a neutrino not as one single particle, but as a trio of distinct personalities. A neutrino born in the Sun, for instance, is always a specific mix of three fundamental mass states. The great unknown is which of these states is the heaviest and which is the lightest. The possibilities are starkly different. In a normal hierarchy, the masses are ordered like a staircase, with two lighter steps and one heavier one. An inverted hierarchy flips this completely, creating a precarious structure where the two lightest states are actually heavier than the third. This is not just a matter of bookkeeping. The structure of this cosmic pyramid scheme dictates how neutrinos behave over immense distances and timescales, including those that make up the ancient cosmic neutrino background. The specific pattern of masses imprinted on these relic particles would create tiny, unique ripples in their energy spectrum, distortions that are like a signature from the first second of time. If we could ever read that signature, it would immediately tell us which hierarchy nature chose. The answer holds the key to one of the universe's greatest imbalances. Why does anything exist at all? The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a universe of pure light. The fact that we are here means something tipped the scales. Neutrinos, with their strange ability to oscillate between types and their mysterious mass, are prime suspects in this cosmic crime. The inverted hierarchy, in particular, opens the door to theoretical processes that could have generated the overwhelming dominance of matter we see today. So, by seeking the faint whispers of the cosmic neutrino background, we are not just studying a fossil. We are looking for the verdict on a cosmic trial, seeking to understand the very rules that allowed galaxies, planets, and us to form from almost nothing. These ancient particles might not be spread evenly across the cosmos. The fourth mystery asks if the cosmic neutrino background has gathered into vast, invisible clouds. Imagine a fine, cosmic dust settling over billions of years, not onto flat surfaces, but into the deepest gravitational wells of the universe. The immense pull of galaxies and the even greater pull of the dark matter halos that surround them could be slowly concentrating these relic neutrinos. Over the eons, gravity's patient tug may have caused them to clump together, creating a denser fog around the largest structures in existence. This is not a simple process. Neutrinos are notoriously slippery, moving at velocities that once approached the speed of light. Their tendency to cluster depends entirely on their tiny yet crucial masses. Heavier neutrinos would slow down more easily, succumbing to gravity's grasp and pooling in these cosmic basins. Lighter ones would remain as a nearly uniform background, sea. Sophisticated computer simulations of the universe's large-scale structure, the great cosmic web of filaments and voids, show this dramatic difference. In one simulation, with a specific neutrino mass, the ancient particles remain a diffuse, evenly spread haze. In another, with a slightly different mass, they flow like a ghostly river into the same galactic nodes that we see with telescopes. The consequence of this clustering is profound. If these neutrinos have gathered around our own Milky Way, the local density of this background could be significantly higher than the cosmic average. For scientists trying to detect them, this would be a game changer. It would be like searching for a rare fish in the entire ocean versus being told they all congregate in a single specific bay. The signal we are straining to hear could be orders of magnitude louder right here in our own galactic neighborhood. This potential clustering ties the fate of the smallest particles directly to the grandest structures. It means the cosmic neutrino background is not just a fossil, but an active, dynamic component of the universe. Its distribution sculpted by the same dark gravity that builds galaxies. Finding these ghostly clusters would not only reveal neutrino masses with precision, it would show us a hidden layer of the cosmic architecture, a shadow structure woven from the oldest threads of reality. This ghostly background sea may hold the ultimate answer to why we exist. The fifth mystery connects the cosmic neutrino background to a pivotal event called leptogenesis, a process that could have saved the universe from vanishing into pure light. In its first moments, the cosmos was a forge of unimaginable energy, creating equal amounts of matter and antimatter. When these two meet, they annihilate in a flash of radiation. For a universe born with perfect balance, this should have been the end, a brief, brilliant existence leaving behind nothing but an empty glow. Something broke that symmetry. Something tipped the scales just 1 part in a billion in favor of matter. And that tiny excess is everything we see today. Leptogenesis is one of the most compelling theories for how this happened. It posits that in the searing heat of the Big Bang, incredibly heavy, as yet undiscovered neutrinos were born. These giants were unstable, and as they decayed, they did so in a slightly uneven way, creating more matter producing particles than antimatter producing ones. This is where a concept called CP violation becomes cosmic. CP violation is a subtle preference nature sometimes shows for matter over antimatter, a tiny bias in the laws of physics. We have seen this in other particles, but for leptogenesis to work, neutrinos must possess a specific, powerful form of this asymmetry. The heavy neutrinos are long gone, but their legacy is written into 2 places: the matter-dominated universe we live in, and the properties of the light neutrinos that remain, the very ones that form the cosmic neutrino background. Observing this ancient sea is our only chance to directly test this grand story. The specific energies and the mix of neutrino types frozen into the background would carry an imprint of those heavy ancestors and their isometric decay. It would be like finding a fossilized gene that reveals the traits of a long-extinct creature. If the pattern matches what leptogenesis predicts, it would confirm one of the most profound events in cosmic history. It would mean that the faint whisper of the cosmic neutrino background is not just a relic, but the very reason there is a universe here to listen. Every particle we know of can eventually die, transforming into something else in a final act of decay. Could the universe's oldest neutrinos be slowly fading away? This 6th mystery confronts a radical possibility that neutrinos might not be truly stable, but possess a finite lifetime. We assume these ghostly travelers from the Big Bang are eternal, but what if they are not? A decaying neutrino would break into even lighter, more elusive particles, perhaps a ghost of a ghost, vanishing from the cosmic sea. The implications for the cosmic neutrino background are staggering. If a significant fraction of these ancient particles has decayed over the last 13.8 billion years, the sea would be thinner and its properties altered. The background would not be a perfect fossil, but a faded portrait missing crucial details. Imagine a vast forest where a certain type of tree is known to live for 1,000 years. If you survey the forest and find far fewer old trees than expected, you might deduce that their true lifespan is actually only 500 years. They are still dying of old age. For neutrinos, this decay is not like a radioactive atom splitting apart. It is a fundamental transformation, a heavier neutrino spontaneously turning into a lighter one and emitting a particle that might be completely invisible to us. This process would leave a distinct signature on the energy spectrum of the cosmic neutrino background, creating distortions and gaps that would be like a fingerprint of their mortality. Current experiments have placed limits, telling us that if neutrinos do decay, their lifetime must be extraordinarily long, far longer than the current age of the universe. But these are limits, not proofs of stability. The theoretical predictions are wide open, with some models suggesting decay times that are almost unimaginably vast. Detecting this decay, or even finding strong evidence for it in the faint whisper of the background, would force a rewrite of the standard model of particle physics. It would mean that even the most fundamental, stable building blocks of reality are, on a cosmic timescale, temporary. The search for this slow cosmic death is a test of permanence itself, probing whether anything from the dawn of time truly lasts forever. Our understanding of the universe is built on a number 3. For decades, evidence from 2 independent cosmic probes has pointed to the existence of exactly 3 types of light-active neutrinos. The first clue came from the universe's first nuclear fusion reactions. In the first few minutes after the Big Bang, protons and neutrons fused to form the earliest hydrogen and helium. The rate and outcome of this process, known as Big Bang nucleosynthesis, are exquisitely sensitive to how many neutrino species were present. More neutrino types would have made the universe expand faster during this critical period, altering the final cosmic recipe. The observed abundance of primordial helium matches the prediction for 3, and only 3 light neutrinos. Billions of years later, a second witness gave the same testimony. The pattern of hot and cold spots in the cosmic microwave background, the afterglow of the Big Bang, is a frozen record of the density waves that rippled through the early cosmos. The characteristics of this pattern are shaped by the relativistic particles, including neutrinos, that were zipping around. Once again, the data fits beautifully with the presence of 3 neutrino species. This number is so foundational, it is woven into the very fabric of the standard model of particle physics. Yet, this elegant picture has developed cracks. A series of perplexing laboratory experiments have persistently suggested a ghost in the machine. For years, data from sources like nuclear reactors and radioactive beams has shown anomalies, small but stubborn discrepancies between the expected and observed numbers of neutrinos. The most tantalizing explanation is the existence of a 4th neutrino, a particle so aloof it does not even feel the weak nuclear force. This hypothetical sterile neutrino would interact with the rest of reality only through gravity, making it nearly impossible to detect directly. It would be a true phantom, a shadow particle. This is where the cosmic neutrino background becomes the ultimate arbiter. If sterile neutrinos are real, and were present in the early universe, they would have left a distinct mark on this ancient sea. A fourth neutrino species would have changed the expansion rate of the universe at a different epoch, altering the precise moment when the relic neutrinos decoupled and froze out. This would have imprinted a unique distortion on the energy spectrum of the cosmic neutrino background, a subtle signature that cannot be faked by anything else. Detecting this background would be like taking a direct census of the particle population from the first second of time. It could finally confirm the sterile neutrino, forcing a monumental rewrite of both cosmology and particle physics. Or it could definitively rule it out, silencing decades of debate and reinforcing the rule of three. The faint whispers of this background hold the power to settle one of the most persistent and fundamental arguments in modern science, revealing whether our universe is built on a trio, or if a fourth, silent partner has been hiding in plain sight all along. The silent conversation between the universe's oldest particles and its most mysterious substance may have sculpted the cosmos we see today. This eighth mystery asks if the cosmic neutrino background is not just a relic, but an active participant, constantly interacting with dark matter. We know dark matter exists because of its immense gravitational pull, shaping galaxies into the vast web we observe. Yet, its true nature remains the greatest unsolved problem in physics. What if the key to understanding it has been flowing through us all along, in the form of these primordial neutrinos? Certain theories propose that dark matter particles are not completely invisible to the neutrino sea. They might engage in a subtle, continuous dance, scattering off these relic neutrinos through some unknown, feeble force. This interaction would be incredibly weak, a mere whisper of a push between two ghosts. But over billions of years, even the gentlest touch can have profound consequences. Imagine a vast, invisible crowd of dark matter particles. Without any other influence, they would naturally clump together, drawn into dense, sharp peaks by their own gravity. This is the prediction of many dark matter models, a cuspy halo with an intensely dense center. However, our astronomical observations tell a different story. The centers of many galaxies appear to have soft, fluffy cores, not the predicted sharp cusps. This is the core cusp problem, a glaring mismatch between theory and reality. The cosmic neutrino background could be the solution. Picture a relentless, gentle wind of relic neutrinos constantly blowing through these dark matter halos. Each tiny scatter, each minor collision, acts like a form of cosmic friction, transferring a little energy outward from the dark matter. This process slowly puffs up the very center of the halo, smoothing out the sharp cusp into the gentle core we actually observe. It would be like a billion years of a soft breeze, slowly eroding the peak of a mountain into a rounded hill. The presence of the neutrino sea provides a constant, universe-wide source of gentle pressure, preventing dark matter from clumping too tightly. For this to work, the dark matter particles themselves would need to be relatively light, allowing the neutrinos to push them around effectively. This elegant idea ties together two of cosmology's deepest mysteries with a single, subtle interaction. Detecting the cosmic neutrino background and measuring its precise properties would give us our first direct test of this ghostly dialogue. If we find that the distribution of these ancient neutrinos carries the unique imprint of being swept along and scattered by dark matter halos, it would not only solve a galactic puzzle, but would finally reveal the identity of the universe's dominant, invisible architect. Hidden within the faint whisper of the cosmic neutrino background could be a record of the universe's first magnetic fields. These are not the familiar fields of stars and galaxies, but something far more ancient and mysterious: primordial magnetic fields born in the chaos of the Big Bang itself. We do not yet know if they truly existed, but if they did, they left their mark on the only thing that was there to feel them: the sea of newborn neutrinos. A magnetic field, even an incredibly weak one, exerts a force on particles that have a property called spin, a tiny inherent magnetism. Neutrinos possess this spin. As these relic neutrinos traveled through the infant universe, a primordial magnetic field would have caused their spins to wobble or precess, like a slow-motion spinning top gradually changing its orientation. This wobble is not just a minor detail, it is a transformation. A neutrino's spin is tied to its identity, to whether it is a neutrino or its antimatter counterpart, an antineutrino. This spin precession could have effectively converted some of these particles from one form to the other as they journeyed across the cosmos. The consequence of this subtle dance would be written into the cosmic neutrino background we hope to detect today. Instead of a perfectly uniform sea, we might find patterns, subtle variations in density and type across different parts of the sky. These anisotropies would be the fossilized imprint of those first magnetic fields. The hunt for these patterns is a hunt for the origin of magnetism itself. Where did the vast magnetic fields that thread through galaxies today originally come from? Were they amplified from tiny primordial seeds? If we can find the signature of those seeds in the neutrino background, it would solve a cosmic chicken and egg problem. This connection stretches even further into some of the most violent events in the modern universe. The theoretical mechanisms that could generate these primordial fields are often linked to the same extreme physics that powers gamma-ray bursts, the most energetic explosions since the Big Bang. By studying the quietest relic, we gain a window into the most chaotic births and deaths of stars. Listening to the neutrino background is not just about hearing a whisper from the past. It is about decoding a magnetic fingerprint from the dawn of time, a hidden force that may have guided the evolution of the cosmos itself. This ghostly sea might itself be unbalanced, hiding a secret preference for matter over antimatter. The 10th mystery probes the possibility of a neutrino-antineutrino asymmetry within the cosmic neutrino background itself, a concept physicists call the neutrino chemical potential. We already know the cosmos favors matter on a grand scale, but this would mean that the bias is etched into the oldest particles in existence. How could such an imbalance arise? In the unimaginable heat of the universe's first seconds, exotic processes beyond our current physics could have actively generated more neutrinos than antineutrinos, or vice versa. This would not be a random fluctuation, but a fundamental skew written into the laws themselves. The consequences of this tiny tilt would have rippled forward in time, leaving marks we can still search for today. The first and most dramatic effect would have been on the universe's first nuclear fusion reactions. The creation of the first hydrogen and helium nuclei in the initial 3 minutes was a delicate dance, exquisitely sensitive to the number and type of neutrinos present. An excess of neutrinos over antineutrinos would have effectively provided more fuel for the nuclear reactions, subtly altering the final cosmic recipe. The fact that our observed primordial element abundances match so well with the predictions for a symmetrical background places a tight constraint on how large this asymmetry could possibly be. It cannot be huge, but it could still be there, a whisper of a whisper. This asymmetry would also have altered the very expansion of the cosmos. An imbalance between particles and antiparticles changes the pressure and energy density of the primordial soup, which in turn dictates how fast space itself stretches. The faintest imprint of this would be left on the large-scale structure of the universe, the great cosmic web of galaxies. Imagine a vast, placid lake. If you pour in a bucket of water that is just slightly warmer than the lake, it will create a barely perceptible current, a subtle disruption in the water's flow. A neutrino asymmetry would have been like that warmer water, creating a tiny but unique signature in how matter clumped together over billions of years. Detecting this would require the ultimate cosmic census, a precise counting of neutrinos versus antineutrinos in the background sea. While our current technology is not yet sensitive enough to perform this count, future experiments aim to look for the unique energy distortions that an asymmetric sea would produce. Finding this imbalance would be like discovering that the universe's oldest fossil is not a neutral record, but a biased account, written by the victor in the ancient war between matter and antimatter. It would prove that the preference for substance over void is not just a feature of the world we see, but a fundamental property of reality itself, frozen into existence at the very beginning. That pristine, uniform sea of relic neutrinos might not be so perfect after all. The 11th mystery focuses on the subtle warps and wrinkles in its energy spectrum, distortions that could be the most revealing features of all. When we picture the cosmic neutrino background, we often imagine a smooth thermal curve, a perfect relic frozen in time from the moment of decoupling. But the real universe is messy, and its history is written in the deviations from that perfect ideal. These spectral distortions are like tiny scars on the fossil, each one telling a story of a violent event or a secret interaction that occurred after the neutrinos were set free. The process of neutrino decoupling itself was not an instantaneous, clean cut. It was a gradual fading away, a final series of interactions that could have left a slight imprint on the spectrum, a gentle bump or dip at specific energies. More dramatic distortions could have been caused by the annihilation of other, unknown particles that filled the early cosmos. As these exotic particles vanished in flashes of energy, they would have dumped heat into the neutrino sea, reheating it just enough to create a noticeable kink in its profile. Or, as we considered before, the slow decay of neutrinos over billions of years would carve a unique gap-like feature in the spectrum. Each of these physical processes leaves a distinct fingerprint. Imagine you have a perfectly smooth, rolling hill. A single event, like a meteorite impact, leaves a sharp crater. A prolonged process, like a slow, steady erosion from wind, creates a different kind of slope. Scientists can model these different distortions, creating a library of cosmic signatures. When we finally capture the true spectrum of the cosmic neutrino background, we will compare it to these theoretical templates. A match would be a direct detection of physics from an epoch we can never otherwise observe. This is why these distortions are such powerful probes for new physics. The standard model of particle physics predicts a nearly perfect thermal spectrum. Any significant deviation is a clear signal that something is missing from our rulebook. It could be evidence for those heavy neutrinos from leptogenesis, for the existence of dark matter particles interacting with the neutrino sea, or for forces of nature we have not yet discovered. The hunt for these spectral warps transforms the background from a simple relic into a dynamic recording of the universe's entire history, a palimpsest where the faintest writing reveals the deepest truths. The universe was not always filled with light. After the cosmic dawn faded, a profound darkness settled in for hundreds of millions of years, a period known as the Cosmic Dark Ages. This silence was shattered by the birth of the first stars and galaxies, whose fierce ultraviolet radiation began to tear apart the neutral hydrogen atoms, filling all of space. This epic transformation, the epoch of reionization, permanently changed the nature of the cosmos. But could that faint sea of relic neutrinos have played a hidden role in this drama? The 12th mystery asks if the cosmic neutrino background was a silent architect of this pivotal age. Theoretically, these ancient particles could have influenced reionization in two profound ways. First, their sheer gravitational presence contributed to the overall pull of matter, helping to draw the first structures together. But more intriguingly, there is the possibility of a direct interaction. If neutrinos scattered off electrons or protons in the primordial gas, even with an unimaginably small probability, they could have transferred a tiny amount of energy. Over the vast expanse of the early universe, this gentle heating could have slightly raised the temperature of the hydrogen gas. Warmer gas is harder to compress and collapse into stars, potentially delaying the ignition of the first cosmic beacons and subtly altering the timeline of reionization. This would have left a specific mark on another cosmic relic we can already see, the polarization of the cosmic microwave background. The pattern of this polarization is a frozen record of the scattering of light by electrons during reionization. A universe where neutrinos actively heated the gas would have a different polarization signature than one where they were completely passive. Our current observations of the CMB polarization already place tight constraints on the reionization process, but they are not yet precise enough to detect the ghostly fingerprint of the neutrino sea. Future observatories, however, will raid this cosmic record with far greater clarity. Finding a mismatch between the observed polarization and the predictions of models that ignore neutrino interactions would be a monumental discovery. It would mean that the universe's oldest particles were not just silent witnesses to the first dawn of starlight, but active participants, their gentle touch helping to shape the very moment the cosmos woke up. The faintest particles in the universe might be carrying messages from the very fabric of spacetime. We are now stepping into the realm where the largest and the smallest scales collide, asking if the cosmic neutrino background could be our only viable telescope for observing quantum gravity. This is the dream of modern physics, a theory that unifies the colossal force of gravity with the probabilistic rules of the quantum world. The problem is that the energy required to see such effects directly is astronomically high, far beyond anything our particle colliders can ever achieve. But the universe has its own natural laboratory, one that ran for 13.8 billion years. The key is in the journey. These relic neutrinos have been traveling for almost the entire age of the cosmos, covering distances so vast they are almost meaningless to the human mind. Over such immense scales, even the tiniest, most subtle effect can accumulate into something detectable. Think of it like a master watchmaker building the most precise clock in existence. In a single second, it keeps perfect time. But if you let it run for 1,000,000 years, you might notice it has gained or lost a few seconds. That tiny, accumulated error reveals a fundamental flaw in its mechanics. The cosmic neutrino background is that clock, and its ticks are the properties of each neutrino. One profound way quantum gravity could manifest is by subtly breaking a sacred principle of Einstein's relativity, Lorentz invariance. This principle states that the laws of physics are the same for all observers, no matter their speed or direction. It is why light always travels at the same speed. But some theories of quantum gravity suggest that at the Planck scale, the absolute smallest size possible, spacetime itself might be foamy or grainy. This granularity could make spacetime act like a medium with a preferred direction. slightly altering the speed of a neutrino depending on its energy. Over billions of light years, a high-energy neutrino might arrive at a slightly different time than a low-energy one, even if they started their journey together. This Lorentz invariance violation would leave a specific smear across the energy spectrum of the neutrino background, a distortion that has no other conceivable cause. Another signature could be quantum decoherence. In the strange world of quantum mechanics, particles can exist in multiple states at once, a phenomenon called superposition. But this fragile state can be disrupted by interactions with the environment. The frothy, microscopic structure of spacetime predicted by theories like loop quantum gravity could itself be that environment, constantly jostling the neutrinos. This would cause them to gradually lose their quantum coherence, to forget their original quantum state. It would be like sending a perfectly tuned chord of music across the universe, only to have it slowly degrade into random noise by the time it arrives. If we detect that the cosmic neutrino background has lost its quantum purity, it would be direct evidence that spacetime has a texture, a physical graininess we can never see, but whose effects we can record. These observations would do more than just confirm an idea. They would tell us which path to quantum gravity is the right one. Does the signature match the predictions of string theory, or does it align better with loop quantum gravity? The ancient neutrino sea is a tape recorder that was running during the universe's infancy, and on it may be the faint, ghostly imprint of spacetime's quantum origins. Listening to its playback could finally answer the deepest question of all. What is the true nature of reality itself? These ghostly particles might be secretly talking to each other. A profound mystery asks whether neutrinos possess their own hidden force, a private channel of communication that could reshape our understanding of the cosmic neutrino background. The standard model of particle physics treats neutrinos as near hermits, interacting so feebly with everything, including themselves, that they are practically solitary wanderers. But what if this is wrong? What if, in the extreme energies of the early universe, a new, unknown force flickered into existence, a force that only neutrinos could feel? This would be a neutrino self-interaction, a ghost whispering to another ghost across the void. The implications for the ancient neutrino sea are dramatic. Such a force would have fundamentally changed how neutrinos behave during their moment of decoupling. Instead of drifting apart silently and individually, they could have remained a cohesive, interacting fluid for a fraction of a second longer. This brief delay would have altered the very moment they froze out from the primordial fireball, changing their final temperature and distribution. The echo of that delay would be imprinted on the spectrum of the cosmic neutrino background we hope to measure today. It would also have left its mark on the large-scale structure of the universe. Neutrinos streaming away from dense regions of dark matter can effectively drag other neutrinos along with them through these self-interactions. This collective motion can smooth out the distribution of all matter in a unique way, potentially solving some of the persistent anomalies in our cosmological data. For instance, there is a long-standing tension in measurements of how fast the universe is expanding today. There is also a curious statistical anomaly in how galaxy clusters are distributed on the largest scales. A background sea of self-interacting neutrinos could provide just enough of a nudge to reconcile these conflicting observations, acting as a subtle cosmic lubricant that adjusts the final structure of the cosmos. The hints for this are tantalizing but fragile. Certain observations of dense astrophysical environments, like the diffuse supernova neutrino background, show patterns that are difficult to explain without some form of neutrino communication. Meanwhile, powerful particle colliders like the Large Hadron Collider are constantly searching for any deviation from the standard model, any sign of a new particle or force that could mediate such a conversation between neutrinos. They have so far found nothing, placing strict limits on how strong this secret force could be. Yet the window for a very weak, almost imperceptible force remains wide open. Discovering this would be like learning that every person in a vast, silent crowd is actually connected by invisible threads, their movements subtly coordinated. For the Cosmic Neutrino Background, it would mean this ancient fossil is not a collection of isolated individuals, but a relic society, its final form shaped by whispers we are only now beginning to suspect. This silent sea of neutrinos is a form of cosmic energy that remains almost entirely unseen. The 15th mystery classifies the Cosmic Neutrino Background as a component of dark radiation, an invisible pressure that helped shape the universe's expansion. We can measure the total amount of this radiation through a cosmological parameter known as the effective number of neutrino species, or NEFF. This number is not a literal head count of particles, but a measure of the total radiation density contributed by all relativistic species in the early cosmos. The standard model prediction is exquisitely precise. NEFF equals 3.046. This tiny amount over 3 accounts for subtle effects like neutrino heating from electron-positron annihilations just after they decouple. This number is not just a theoretical curiosity. It is a fundamental part of the cosmic recipe that determines how fast the universe expanded during its first few 100,000 years. The afterglow of the Big Bang, the cosmic microwave background, carries a frozen record of this early expansion rate. When we analyze its patterns, we can extract a measured value for NEFF. And here lies a growing tension. Some of the most precise measurements from observatories like the Planck satellite suggest a value that is slightly higher than the standard model prediction, hinting at the possibility of extra dark radiation. Imagine the early universe as a pot of water coming to a boil. The standard model tells us exactly how much heat or radiation should be in that pot. But our measurements of the cosmic microwave background are like checking how vigorously the water is bubbling, and the bubbles seem just a little too active, suggesting there might be a hidden source of heat we did not account for. This is where the Cosmic Neutrino Background becomes the central suspect. If we could directly detect it and measure its true properties, we would know for certain if it alone is responsible for the radiation density, or if something else is lurking in the background. This mystery is not isolated. It is deeply entangled with one of the biggest controversies in modern cosmology, the Hubble tension. This is the stubborn disagreement between measurements of the universe's current expansion rate, the Hubble constant, taken from the early universe versus those taken from the nearby modern universe. An increase in NEFF, meaning more dark radiation in the early cosmos, would have changed the timing of key events, altering the inferred expansion rate from the early universe in a way that could potentially bring it into alignment with the faster rate measured today. The Cosmic Neutrino Background is the missing piece that could solve this puzzle. Is the slight excess in radiation density real? And if so, is it because the relic neutrinos themselves have unexpected properties? Or is it evidence of a completely new light particle that has since vanished? Direct detection of this ancient sea would provide an absolute calibration for NEFF, turning an inferred parameter into a measured quantity. It would tell us if the universe's engine ran with a little extra ghostly fuel from the very beginning. a hidden push that has guided cosmic evolution for billions of years. This ancient sea of neutrinos is not perfectly smooth. Just as the cosmic microwave background shows a modeled pattern of hot and cold spots, the cosmic neutrino background must also be imprinted with its own unique anisotropies, a faint fingerprint of the universe's earliest structures. These are not random imperfections. They are a direct record of the gravitational struggles that shape the cosmos. In the first few 100,000 years, the universe was a patchwork of slightly dense and slightly empty regions. The denser patches, packed with dark matter, created deeper gravitational wells. As a relic neutrino streamed through one of these wells, it had to climb out, fighting against the pull of gravity. This cosmic effort cost it energy, leaving it slightly colder and slower once it escaped. Conversely, a neutrino falling into a well would gain energy, becoming slightly hotter. This process, known as the Sachs-Wolf effect, creates a pattern of hot and cold spots in the neutrino background that perfectly mirrors the underlying dark matter distribution of the infant universe. It is like a cosmic relief map, where the valleys are marked by colder neutrinos and the hills by warmer ones. But there is a crucial difference between the neutrino map and the light map we already have. The cosmic microwave background photons were released all at once, giving us a single snapshot of the universe at 380,000 years old. The cosmic neutrino background, however, is a cumulative film. These particles have been streaming freely since the first second, and they have continued to be subtly red-shifted and blue-shifted by every gravitational hill and valley they have encountered over nearly 14 billion years. The final pattern we would detect today is a palimpsest, a layered image containing information from the very first structures all the way to the modern cosmic web. Mapping these anisotropies would be the ultimate test of our theories of structure formation. The specific statistical properties of the hot and cold spots, their size and distribution, would tell us precisely how dark matter clumped together over time. It would also reveal the masses of the neutrinos themselves with unparalleled precision. Heavier neutrinos, being slower, would be more susceptible to the pull of these gravitational potentials. They would cluster more strongly, creating a sharper, more pronounced pattern of anisotropies. Lighter neutrinos would barely notice the hills and valleys, resulting in a much fainter, more washed-out map. Future surveys that could correlate this neutrino map with observations of galaxy clusters would give us a dynamic view of cosmic evolution, showing how the invisible scaffolding of dark matter directly guided the formation of everything we see. We would no longer be inferring the presence of dark matter. We would be watching its gravitational shadow move and grow across the eons, traced by the oldest particles in existence. This faint, ghostly relief map is a hidden layer of cosmic history waiting to be read. That moment of cosmic separation was not a clean break. Roughly 1 second after the Big Bang, the universe underwent a profound divorce as the vast sea of neutrinos drifted free from the primordial plasma. This event, neutrino decoupling, is the very reason the cosmic neutrino background exists. Yet the precise mechanics of this split remain shrouded in mystery. It was a time of incredible transition. The universe was still an opaque, seething soup of particles, 1 billion times denser than water and hotter than the core of any star. Electrons, positrons, and photons were locked in a violent, constant dance of creation and annihilation. The neutrinos, which had been active participants in this chaos, were beginning to lose their grip. As the cosmos expanded and cooled at a ferocious rate, the rate of interactions between neutrinos and other matter plummeted. the average distance a neutrino could travel without a collision. Its mean free path stretched longer and longer until it effectively became infinite. The particles simply stopped seeing the rest of the universe. This was not an instantaneous event for every neutrino, but a gradual fading away across the entire population. The final interactions of this fading era are critical. Even after the majority of neutrinos had decoupled, the very last collisions could have left a subtle imprint on their energy spectrum. It is like a crowd of people slowly leaving a noisy party. The main roar of conversation dies down, but the final few words spoken at the door can still change the mood of those departing. In this case, the final annihilations of electron-positron pairs dumped a little extra energy into the photon bath, reheating it. The neutrinos, already mostly detached, missed out on this extra heat. This tiny thermal snub is precisely why the cosmic neutrino background is calculated to be colder than the cosmic microwave background. But what if this story is incomplete? The possibility of slight delays or even brief recouplings hangs over this entire narrative. If new physics, like those secret neutrino self-interactions, were at play, the decoupling process could have been prolonged. The neutrinos might have remained a cohesive fluid for a fraction of a second longer, exchanging energy amongst themselves and maintaining a different temperature profile. Alternatively, an unknown, heavy particle decaying during this critical window could have re-injected energy, temporarily recoupling the neutrinos to the plasma and scrambling the pristine snapshot we expect. The implications of such a disturbance would be written into the universe's first elements. The process of Big Bang nucleosynthesis, which forged the primordial hydrogen and helium, is exquisitely sensitive to the conditions during this first second. The expansion rate of the universe, which governs how quickly protons and neutrons can fuse, is directly affected by the number and energy of relativistic particles like neutrinos. A delay in decoupling would have changed that expansion rate, subtly altering the final cosmic recipe of elements we observe today. This makes the observed abundances of light elements a powerful, indirect probe of that long-vanished epoch. The cosmic neutrino background is the only direct witness to these events. While the cosmic microwave background shows us the universe at 380,000 years old, the neutrino background is a fossil from its first second of independent life. Its properties are a unique snapshot of the instant the neutrinos went silent. Measuring its true temperature and spectrum is not just about confirming a prediction. It is about replaying the tape of that cosmic divorce in ultra-slow motion. Any deviation from the expected profile would be undeniable evidence that the separation was messier, more complex, and far more interesting than our standard models suggest, revealing a hidden chapter in the universe's very first breath. One of the greatest controversies in modern cosmology hinges on a simple number, the Hubble constant, which measures how fast the universe is expanding today. The problem is, we have two different ways of measuring it, and they stubbornly refuse to agree. Measurements based on the early universe, using the cosmic microwave background, give one value. Observations of the nearby cosmos, using supernova and other markers, give a consistently faster rate. This is the Hubble tension, a gap that suggests something fundamental is missing from our cosmic model. The ghostly presence of the cosmic neutrino background could be the missing piece that bridges this divide. The key lies in a feature called the sound horizon. This is the frozen imprint of the largest sound wave that could travel through the primordial plasma before the universe became transparent. It acts as a universal standard ruler, a fixed measuring stick we used to gauge distances in the early cosmos, and from there, calculate the expansion rate. The size of this sound horizon is exquisitely sensitive to the contents of the early universe, particularly to the amount and behavior of dark radiation, which includes our relic neutrinos. If the properties of the cosmic neutrino background are different than we assume, if the neutrinos were slightly more interactive or had a different energy density, it would have altered the speed of sound in that primordial soup. This, in turn, would change the measured size of the sound horizon. A smaller sound horizon from the early universe would make the inferred expansion rate faster, potentially bringing it into line with the faster rate we see today. It is like trying to measure a room with a ruler you thought was 12 inches long, only to discover it was actually only 11 inches. Your initial measurements of the room would be wrong. Correcting the ruler's length fixes everything. Researchers are now building sophisticated cosmological models that tweak the properties of the relic neutrino sea, exploring whether a slight adjustment can make the early and late universe measurements snap into perfect alignment. This is not just a theoretical exercise. It is a direct test of whether the oldest particles in existence are quietly holding the universe together, their faint whisper containing the secret to its expansion. Solving the Hubble tension would be more than a technical triumph. It would confirm that we are finally listening to the cosmos correctly, hearing the full story written in both its ancient light and its oldest ghosts. The most violent explosions in the cosmos are constantly firing ghostly bullets at the relic neutrino sea. When a star explodes in a supernova or a black hole shreds a star, it can launch neutrinos with energies millions of times greater than those frozen in the cosmic neutrino background. These high-energy travelers do not journey alone. They must pass through the vast, tenuous fog of the ancient relic neutrinos, and on rare, spectacular occasions, they collide. This is not a gentle meeting. When a high-energy neutrino from a distant cataclysm smashes into a low-energy relic neutrino, the result can be the creation of a new, short-lived particle, like a Z-boson. This event, known as the Z-burst, is a miniature recreation of Big Bang energies, annihilating both neutrinos in a flash of other particles. For the high-energy neutrino, it is the end of the line. Its journey is cut short, its signal erased before it can ever reach our detectors. This resonant scattering creates a shadow in the high-energy neutrino sky, an absorption line that corresponds precisely to the mass of the relic neutrinos. Finding that shadow would be a direct and breathtaking measurement of the neutrino's mass. This process is part of a broader cosmic censorship known as the Greisen-Zatsepin-Kuzmin cutoff. Ultra-high-energy cosmic rays, which are protons and atomic nuclei, also interact with the relic background, but they do so with the cosmic microwave background photons. As these incredibly energetic particles travel across the universe, they lose energy by creating new particles, effectively putting a cap on the maximum energy we should observe from distant sources. The exact location of this energy cutoff is a sensitive probe of the universe's particle content, including the density and distribution of the relic neutrino sea. If the relic neutrinos have clumped around our galaxy, as some theories suggest, the local fog would be denser, making these high-energy collisions more likely and further sculpting the spectrum of particles we can observe. This transforms the entire field of multi-messenger astronomy. We are no longer just looking at light. We are listening for gravitational waves and catching these high-energy neutrinos. When we detect a high-energy neutrino from a specific direction in the sky, its energy tells a story. If its energy is lower than expected, it may have encountered a dense pocket of relic neutrinos on its way here, a ghostly cloud we can map through its absorption effect. The ultimate dream is to correlate a high-energy neutrino event with a specific astrophysical source, like a blazar, and then use the properties of the neutrino to probe the invisible sea it passed through to get to us. Each of these cosmic messengers becomes a probe, its journey a measurement of the ancient background that fills all of space. The universe is using its most energetic events to illuminate its quietest relic, painting a picture of the cosmic neutrino sea with strokes of unimaginable power. The universe's accelerating expansion is powered by a profound enigma known as dark energy, often represented by the cosmological constant. This mysterious force is woven into the fabric of space itself, pushing galaxies apart at an ever-increasing rate. But what if this cosmic push, this dark energy, is not a fundamental property of the vacuum, but a ghostly echo of the oldest particles in existence? The theoretical connection between the cosmological constant and the cosmic neutrino background is one of the most speculative and breathtaking ideas in modern physics. It hinges on the concept of vacuum energy, a seething sea of virtual particles that constantly pop in and out of existence, even in empty space. According to quantum field theory, every particle, including neutrinos, contributes to this background energy. The problem is, when physicists calculate the total vacuum energy from all known particles, the result is a number astronomically larger than the tiny value of the cosmological constant we observe. This is the famous cosmological constant problem, a discrepancy of over 100 orders of magnitude, the worst prediction in the history of science. The relic neutrino sea might offer a way out of this impasse. One compelling idea is that the universe's expansion itself affects how neutrinos contribute to the vacuum. As space stretches, the energy density of the cosmic neutrino background drops in a specific way. Some theories suggest that this evolving background could effectively cancel out the enormous vacuum contributions from other particles, leaving behind the small, positive value we measure as dark energy. It would be a cosmic coincidence of unimaginable precision, a cancellation act orchestrated over billions of years, leaving just the right amount of repulsive gravity to drive the acceleration. Another, even more radical, proposal is that the neutrinos themselves are intimately tied to the mechanism behind dark energy. Could their unique properties, frozen into the background, be directly responsible for the cosmological constant? Testing these ideas is extraordinarily difficult, but not impossible. The key lies in how the equation of state of dark energy, the relationship between its pressure and density, has changed over cosmic time. Our standard model assumes the cosmological constant is truly constant. But if the relic neutrino sea is driving it, there might be a subtle evolution, a slow drift in its strength that mirrors the cooling and thinning of the neutrino background. Future precision measurements of the expansion history, from projects like the Euclid Space Telescope or the Vera-C Rubin Observatory, will hunt for any deviation from a pure cosmological constant. They will look for the faintest whisper of change in dark energy's push. If such a drift is found, and if it matches the predicted influence of the cosmic neutrino background, it would mean that the acceleration of the universe is not a lonely, fundamental force, but a dynamic conversation with the oldest fossil in existence. The ghost sea would then be more than a relic. It would be an active engine of cosmic destiny. These ghostly particles have a secret identity crisis. A neutrino born in the heart of the sun can transform into a different type by the time it reaches Earth, a quantum phenomenon known as oscillation. This constant, flickering dance between identities is not just a feature of modern neutrinos. It is a property that must have been active in the universe's first second. The 21st mystery asks how this flavor mixing imprinted itself on the cosmic neutrino background, and whether its ghostly signature can still be found today. The early universe was a far more extreme environment than anything we can replicate. It was unimaginably dense, a hot soup where particles were packed so tightly that their quantum waves constantly overlapped. In such a crowd, the simple act of a neutrino changing from an electron neutrino to a muon neutrino could have been a collective event, influenced by the presence of billions of other neutrinos all around it. This is known as collective oscillation, a synchronized dance where the entire sea of particles changes flavor together, like a vast school of fish turning in perfect unison. This collective behavior would have frozen into the cosmic neutrino background as a specific and potentially measurable ratio of the three neutrino flavors. We assume the background is an even mix of all three. But what if the frantic oscillations of the early universe locked in a different recipe, one with more tau neutrinos and fewer electron neutrinos? That final flavor composition is a fossilized record of the universe's density in its first moments. The consequences of this primordial mixing ripple forward through time. The different neutrino flavors interact with matter in slightly different ways. An electron neutrino, for instance, plays a unique role in nuclear reactions. If the cosmic neutrino background had an overabundance of one flavor, it could have subtly altered the process of Big Bang nucleosynthesis, changing the final amounts of hydrogen and helium that were forged. This means the primordial elements we observe today might carry a faint, indirect hint of that ancient neutrino dance. This cosmic mystery is now being pursued in laboratories deep underground. Experiments like the Deep Underground Neutrino Experiment and T2K are precision instruments designed to study neutrino oscillations over long distances. They are creating intense beams of a single neutrino type and watching carefully as they transform on their journey to a distant detector. By mapping the precise probabilities of these changes, they are essentially reverse engineering the rules of the oscillation dance. The data they collect feeds directly into our models of the early universe, allowing us to simulate with greater and greater accuracy how that vast primordial sea must have behaved. The ultimate goal is to predict the exact flavor map of the cosmic neutrino background. When we finally build a detector capable of tasting this ancient sea, the first thing it might tell us is not just that neutrinos are there, but what kind of neutrinos they are. If the flavor ratio matches the predictions from our laboratory experiments, it will be a stunning confirmation that we understand quantum mechanics on a cosmic scale. If it does not, it will reveal that the universe's first environment was so extreme that the rules of the dance were different, pointing toward physics we have not yet discovered. The faint whisper of the background is not just a monotone hum, but a chorus of different voices, and learning to distinguish them will reveal the secret social lives of the universe's oldest particles. These frozen sound waves from the dawn of time are imprinted across the entire cosmos. The 22nd mystery examines the silent partnership between the cosmic neutrino background and the phenomenon known as baryon acoustic oscillations. To understand this, you have to go back to the universe's first few 100,000 years. It was a searing plasma, a fluid of light and matter so dense that pressure waves, literal sound waves, raced through it. These were not gentle ripples, but the most colossal tsunamis imaginable, stretching across hundreds of thousands of light years. Dark matter, unaffected by light's pressure, simply sat at the center of these waves, forming the gravitational core. The ordinary matter, protons and electrons, was trapped in a fierce tug of war. The intense radiation pressure from the light tried to push it outward, while gravity from the dark matter centers tried to pull it back in. This created a spherical sound wave that expanded outwards from every initial density fluctuation, like a ripple spreading from a stone dropped in a pond. When the universe cooled enough for atoms to form, a moment known as recombination, the light suddenly broke free, and the pressure wave stopped in its tracks. The matter that was at the leading edge of that wave, the crest of that cosmic ripple, was frozen in place. This is the Barrian acoustic oscillation. It left a specific, predictable signature, a preferred distance between galaxies. We can see this fingerprint in massive galaxy surveys today. A statistical excess of galaxy pairs separated by about 500 million light-years, the radius of that ancient sound wave. This distance acts as a standard ruler, a cosmic tape measure we can use to track the expansion history of the universe with incredible precision. So where do the ancient neutrinos come in? That primordial sea was present during all of this. While neutrinos interact too weakly to feel the radiation pressure directly, they are massive, and their gravity contributes to the overall pull of the universe. More importantly, their presence and behavior change how fast the sound wave could travel through the early plasma. The speed of sound in that primordial fluid depended on the ratio of radiation to matter. The cosmic neutrino background was a significant part of that radiation budget. If its properties were different than we assume, if the neutrinos had a slightly different energy density or were interacting with each other, it would have altered the speed of that sound wave. A faster wave would have traveled farther before freezing, creating a larger standard ruler. A slower wave would have created a smaller one. When we use galaxy surveys to measure the apparent size of this ruler at different cosmic epochs, we are indirectly measuring the properties of the neutrino sea that influenced its creation. This is crucial for our understanding of dark energy. The rate at which the apparent size of this standard ruler changes over time tells us how the universe's expansion has accelerated. Any miscalibration in the ruler's true size, caused by a misunderstanding of the neutrino background, would lead to an incorrect measurement of dark energy's strength and evolution. By directly detecting the cosmic neutrino background, we could remove this uncertainty. We would know the exact contribution of these relic particles to the early universe's energy content, allowing us to perfectly calibrate our cosmic tape measure. This would turn Barrian acoustic oscillations into an even more powerful probe, sharpening our constraints on dark energy and potentially revealing if its push has changed over the life of the cosmos. The faintest particles in existence are holding the other end of the universe's most important measuring stick. Our universe might be a membrane floating in a higher dimensional reality. This startling concept, known as the brain-world scenario, proposes that the three spatial dimensions we experience are not the whole story. Hidden dimensions could be curled up or extended just beyond our perception, and the cosmic neutrino background might be the only thing that can cross that boundary. In some versions of this theory, most particles, like electrons and quarks, are stuck to our brain, our slice of reality. But neutrinos, the ultimate ghosts, are different. They could be the only known particles that are not confined. They might be able to leak out, propagating through the unseen bulk of these extra dimensions. This cosmic escape would have profound consequences for the ancient sea of relic neutrinos. If neutrinos can travel through more dimensions than we can, their fundamental properties would appear different from our three-dimensional perspective. The effective mass we measure for them would not be their true mass, but a kind of shadow, a projection of their higher dimensional nature onto our brain. This could elegantly explain why neutrino masses are so inexplicably small compared to every other massive particle. They are not small, they are just diluted across dimensions we cannot see. The journey through the bulk would also open up new ways for these particles to interact and lose energy, potentially leaving a unique distortion in the spectrum of the cosmic neutrino background. Imagine you are listening to a choir in a sealed room. The sound is clear and contained. Now, imagine that room has a hidden door left ajar. The sound would leak out, and the choir's voice inside the room would sound slightly fainter, slightly different. The cosmic neutrino background is that choir, and any unexpected faintness or warble in its signal could be the sound of its song leaking into other dimensions. This is why any future anomaly in the background's properties would be so electrifying. If its temperature, density, or flavor composition does not match the precise predictions of our standard three-dimensional models, it could be the first tangible evidence that our universe is a much, much bigger place than it appears. We would have proof that reality has hidden layers, and that the oldest, quietest particles in existence are our only guides to this grander cosmic architecture. The universe's most destructive objects might be leaking their secrets into its quietest sea. Black holes present a nightmare for physics, a paradox that strikes at the heart of reality. According to Einstein's general relativity, a black hole's event horizon is a point of no return, a one-way membrane that swallows everything, including information about what fell in. Yet quantum mechanics insists that information can never be truly destroyed. This is the black hole information paradox, a fundamental conflict between our two most successful theories. Where does the information go when matter is consumed by a singularity? The answer might be written in the faint, pervasive static of the cosmic neutrino background. One radical proposal suggests that the process of black hole evaporation is not perfectly clean. As a black hole slowly radiates away its mass through Hawking radiation, it might not emit a featureless glow. Instead, subtle correlations in that radiation could encode the information about what fell in, like a slow, careful broadcast of the black hole's entire history. But broadcasting to whom? The signal would be imprinted on the most fundamental medium imaginable, the fields that permeate the vacuum of space. And the most sensitive witnesses to those fields are the lightest, most abundant particles in existence, the neutrinos of the cosmic neutrino background. These relic particles, constantly streaming through the cosmos, could be subtly altered by this information-rich radiation. Their quantum states might be entangled or shifted in a way that preserves a record of the black hole's demise. The ancient neutrino sea would then act as a cosmic hard drive, storing data from the most violent events in the universe. This idea stretches back to the universe's infancy. The first seconds after the Big Bang may have spawned countless primordial black holes, tiny and incredibly dense. If these mini black holes evaporated through Hawking radiation in the early cosmos, they would have dumped a flood of particles and information directly into the nascent neutrino background. The specific distortions in the energy spectrum of the cosmic neutrino background that we hope to one day measure could be the scrambled, fossilized record of those first black holes dying. Listening to the backgrounds, whisper could be like recovering fragments of a lost library from the dawn of time. This connection ties the fate of the largest structures to the smallest particles in a profound new way. It suggests that information is not lost but translated, moved from a manifest state we can see, like a star, into a latent state woven into the fabric of the ghost sea. Verifying this is, for now, beyond our reach, but the principle is what matters. It positions the Cosmic Neutrino Background as the ultimate archive, a medium that might hold the answer to whether the universe truly forgets anything, or if every event, no matter how catastrophic, leaves an eternal, if nearly imperceptible, mark on reality. The universe's oldest story is still being written, and its final chapter will be one of fading and isolation. As the cosmos continues its relentless expansion, the very fabric of space stretches, and with it, the wavelength of every relic neutrino grows longer. This cosmic redshift drains their energy, cooling the background sea to temperatures that approach absolute zero. What is now a faint whisper will become an almost inaudible sigh, a ghost of a ghost. In the far future, the energy of these particles will be so minuscule that the concept of detecting them may become physically impossible, not just technologically challenging. The universe will have effectively erased its own oldest fossil. This slow fade carries a profound philosophical weight. The cosmic neutrino background is the most enduring direct relic of the Big Bang, a constant presence through the entire history of everything. It witnessed the formation of the first stars, the birth of galaxies, and the rise of life. Its gradual disappearance into the cold, dark emptiness of the expanding cosmos marks the end of an era, the final severing of our tangible connection to the moment of creation. It prompts us to consider our own fleeting moment within this grand timeline. We exist in a special cosmic window, a time when the universe is old enough to have produced complex structures like planets and life, but young enough that the echoes of its birth are still, just barely, within our reach. Future civilizations, if they arise in a universe billions of years older, may never know this direct link to their origins. They might infer the Big Bang from the retreating galaxies, but the primordial neutrino sea, the last messenger from the first second, will have fallen silent for them. Our current quest to detect this background is therefore more than a scientific endeavor. It is a race against cosmic time. We are reaching out to grasp a memory before it fades forever. The enduring legacy of the Big Bang is not just the universe it created, but the knowledge that we were here, in this brief, luminous moment, to listen to its story and understand our place within it. Each of these 25 mysteries reveals a universe far stranger than it appears, a cosmos built not just on light and matter, but on the whispers of its oldest ghosts. From the simple, profound challenge of detecting this faint sea, to its precise temperature and the secret identity of its neutrino masses, each question forces us to reconsider our most basic laws. We have explored how its potential clumping could map invisible dark matter, how it might hold the answer to our existence through leptogenesis, and whether its particles are eternally stable or slowly fading away. The puzzle of a possible fourth neutrino species challenges the very foundations of particle physics, while its potential conversations with dark matter could solve galactic riddles. Primordial magnetic fields may have left their fingerprint upon it, and a hidden matter-antimatter asymmetry could be frozen within its core. The subtle warps in its energy spectrum are a record of cosmic violence, and its role in the epoch of reionization suggests it was an architect of the first starlight. It serves as our only viable telescope for the quantum foam of spacetime, and the possibility of its own secret force hints at a hidden social network among these particles. As a component of dark radiation, it fuels the Hubble tension, and its own anisotropies form a hidden relief map of cosmic structure. The precise mechanics of its decoupling from the primordial plasma remain a pivotal unknown, and its influence on baryon acoustic oscillations calibrates our cosmic rulers. The radical notion that neutrinos might leak into extra dimensions opens a door to a grander reality, while their connection to the black hole information paradox suggests this sea is the universe's ultimate archive. Finally, its inevitable fading in the far future marks the end of our direct link to creation. This is not a mere list of curiosities. Every single mystery represents a fundamental frontier, a point where our current understanding of physics meets a wall of pure mystery. The quest to detect and study the cosmic neutrino background is our most ambitious attempt to listen to the universe's first breath, to decode a message sent when time itself was young. It is a journey that will redefine reality. We want to know which of these 25 mysteries captured your imagination the most. Was it the connection to dark matter, the solution to the matter-antimatter mystery, or the mind-bending possibility of extra dimensions? Share your thoughts in the comments below. For more deep dives into the universe's greatest secrets, make sure to subscribe. The cosmos has countless stories left to tell, and the next one is